Welcome to a quick review of Chapter 1 for Intermediate Algebra. We're going to be evaluating expressions here to get started. And again, this is designed to be a review, so I will be moving quickly. As always, feel free to use the pause function, go back and rewind and rewatch if you need to later on. But we have this algebraic expression right here, y squared plus the square root of x plus 7, all over absolute value of 3x minus y, and we're going to evaluate this expression when x is 9 and y is 2. So remember that when we're saying evaluate the expression, we're really just saying find the values that they give you and plug them in or substitute them in where they belong. So for example, wherever the y exists in my expression, I'm going to insert the negative 2. So I'm going to start by rewriting this as, instead of y squared, it'll be negative 2 squared. Then I'll have plus the square root of, and then I have an x right there. That x right there, and I'm going to replace that x with what x equals. So it'd be 9 plus 7, all over absolute value of 3. And then I have to remember, so when that is 3x, I'm recalling that in between there, between the 3 and the x, is implied multiplication. So it's 3 times x. So I'm going to write 3 times 9. And then minus y, and the y value is negative 2. Notice I'm also putting everything in first. I'm not trying to simplify anything until I've inserted everything. If you get in the habit of trying to simplify too soon, you oftentimes miss elements as you move along. So then I'm going to go through and I'm going to start thinking, what can I do or what should I do first? And this is jogging your memories back to this. If you've seen it before, PERMDAS. Many of you may have learned it as PEMDAS, but this stands for you do what's in parentheses first, followed by what's in the exponents, followed by roots and radicals, then multiply, divide, add, then subtract, in that order. So I'm going to start with parentheses, and again, we don't have any specifically designed here, but we have implied parentheses underneath the square root and inside of the absolute value, which means I can do what's inside the square root first. So I'll have negative 2 squared plus the square root of 16 all over, and then I can do what's inside of the absolute value, and there's multiple things going on inside the absolute value, so that's where I go, okay, there's no exponents, there's no radicals and roots, but there is multiplying, so multiplying happens next. So then I have 3 times 9, that gives me 27, and then after that I have adding and subtracting going on. I have minus a negative 2. Minus a negative 2, negative times a negative is positive, so this is then plus 2. As I keep going here, I'm going to simplify more. In the numerator, then I have removed all of my parentheses. Now I can do exponents. Negative 2 squared. Squared means times itself, so negative 2 times negative 2 is 4. Plus the square root of 16. What number times itself is 16? That is also 4. In the denominator, I have the square root of 29, absolute value. So I have 8 over 29 as my final answer. Moving on. Number systems, this is going maybe way back in your math career, and maybe you haven't been talking about this in a long time, but we're just going to go through a refresher of what these are. Natural numbers are numbers that would occur naturally, or you think in nature. So it's like counting numbers. So natural numbers start with the number 1, and then they go to 2, and then 3, and then 4, etc., etc., etc. They are counting numbers. Whole numbers is my next set. The difference is now we include 0, because think of like, well, how many whole apples can you have? I can have none, 1, 2, 3, or 4. Natural numbers are when we're looking at things in nature. If we say I have 0 of something, you can't represent 0 naturally. I could say, hey, this is 0 apples, and you could say that that's 0 oranges. It's no different. Whole numbers is then counting how many of something we have. Integers, we take whole numbers and we expand it up to, and again, they're going to be going up by 1, and the positive and negative. So sometimes people consider integers to be positive and negative whole numbers. Rational numbers, now we're going to get a little bit more and less in terms of writing as a set here, but rational numbers are numbers that can be expressed as a fraction using integers. So, for example, negative 0.25 is a rational number because it can be, I should not have this as an equal. I'll give you an example of a rational number. 0.25 is equal to negative 1/4. It can be represented as a ratio. That's why the word is rational. It's a ratio, R-A-T-I-O. It's a ratio or a fraction of two integers. If I had 0.3 repeating, 0.3 repeating can be listed as 1/3. It's a ratio of two integers. Irrational numbers are numbers that cannot. The square root of, sorry, I'll make that there. The square root of 5 is going to be a repeating decimal that cannot be, it's a non-repeating decimal that cannot be expressed as a fraction of two integers. Therefore, it's considered irrational. And then the last one's transcendental. We're not going to spend a lot of time going through a definition. You've got numbers like pi, 3.141592, et cetera, et cetera. We'll talk a little bit later about the number e. These are just probably the most two common transcendental numbers that exist out there as we talk about number systems. Set notation. Again, this is going to depend on your background in mathematics as to whether or not you've had an instructor use set notation before. Some call it just a simpler way to go through it. I really look at it and say set notation is because mathematicians were lazy and we don't want to write out all the words. So we come up with ways of saying the set of all x's such that x is a natural number greater than 10. All right, so what would that mean? If I actually were to list that one out, this set would be all the natural numbers greater than 10. All right, so I don't start at 10, I would start at 11 because greater than 10, and there'd be 12, 13, comma, et cetera, all the way up to infinity of natural numbers. The second string right here, if I would read this, it says 3 is an element of the set negative 2, 1, 3, and 7. Simply meaning that if I look at this set of numbers, is 3 a part of that set? If the answer is yes, then 3 is an element of that set. Down here, I have a set with negative 2, negative 1, and 7. Is 3 an element of that set? No, it's not. So we say it's not an element of. And then if I use the information that from the previous page, I could say natural numbers, and you're going to see it sometimes written like this. Natural numbers is a subset of our integers. And you're going to say, why is it z? It just is. Go with it. There's different things that we'll use. When I'm talking about real numbers, I'll be talking about this. So n natural numbers is a subset of all integers. So that just simply means that if I look at all of the integers, all of n exists somewhere inside of here. I wouldn't quite say it as an element of, because when I'm talking about element, I'm looking at is something a part of another set. Then we've got the difference between an expression and an equation. An expression is going to be something like this. It's a word model for something that we're going to do mathematically. In this case, if I were to take this and translate it, I'd say 8 more than a number doubled. That's an expression. Expression is like a phrase in English. It's not a complete sentence. An expression is a phrase. An equation gets us to a little bit differently. Now we have this, so we take and we start translating. It says 4, so I'm going to translate that as 4, is, all right, we only have is, just is as a straight up means equals, 8 more than a number doubled, 2x. This is a complete sentence, and if you even read it, if you have a background in English, 4 is 8 more than a number doubled. We have subject, object, verb. We have a complete sentence. 8 more than a number doubled is not a complete sentence. There's no connection to it, no verb going on. The is my equal sign. And that is can be is greater than, is less than. If we just say is, we mean is equal to. So an expression is here. It can be simplified. An equation can be simplified and solved. So we could actually calculate and find that value for x. Quick review of square roots. Square root of 9 would means what number times itself is 9? That would be 3. Square root of 27, there isn't a number that we know. Usually what I like to do when I'm getting started with this is just write down all my squares quickly. So 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared. You can keep going down, but you get the idea there. 27 is not on that list. However, there is a number on this list that divides evenly into 27. So a square root can be split up with values that are multiplied to. So for example, 27 can be rewritten as the square root of 9 times the square root of 3. I choose 9 because I know the square root of 9. The square root of 9 is 3. So it'd be 3 times the square root of 3, or oftentimes we would just leave it written as 3 root 3. And then this next one here, this simply means cube root, which means what number times itself 3 times is equal to 27. Or sorry, I should probably do it like this. Blank, blank, blank equals 27. And if I know what that is, then it will be just that single blank. 3 times 3 is 9, times 3 is 27, which we just had up top. So the cube root of 27 is 3. Because multiplication is possible to split up the square root, I can do the same thing with division. So I can have the square root of 1 over the square root of 4, so that will then be 1, square root of 1. What number times itself is 1? That's just 1. What number times itself is 4? And that's 2. It cannot, so I cannot do this. Oh, sorry, cannot do square root of 4 plus the square root of 9. This is an absolute no, not possible. The only thing you can do inside is I could say the square root of 4 plus 9 is equal to the square root of 13. And that is all. And then down here, we're asking ourselves what number times itself is negative 64. We oftentimes are going to look at this and say, it's 8. But 8 times 8 is 64. And then some people say, well, what if it's negative 8? Negative 8 times negative 8, negative times a negative is also 64. And the answer is here, there is no real solution. We don't say it doesn't exist because technically there is an answer to that. It's just not a real solution. It will be an imaginary solution, and that's for a course later on. Quick review, 5 squared means 5 times 5, which is 25. 5 cubed means 5 times 5 times 5, which is 125. Negative 5 cubed means negative 5 times negative 5 times negative 5, which is negative 125. Negative times a negative times a negative, 3 negatives, negative 1 times negative 1 times 3 negatives, this still remains negative. Be careful with your calculators. If you get to something like this and you type in negative 5 to the 4th, your calculator will give you a negative answer because your calculator is oftentimes not very smart. Negative 5 to the 4th should be and is a positive number, not a negative number. We look at that there quick, and we're going to just jump into this, much like we did before with going with our order of operations. Simplify this, so I'm going to have negative 5 times the square root of 25 plus, and then I'm going to go ahead and do that first one. Negative 2 squared is negative 2 times negative 2, which is 4. At the denominator, I'll have 16 plus 7 minus 10 is negative 3. In the numerator, I then have negative 5 times 5, because the square root of 25 is 5, plus 4, all over 16 plus 3. Remember, when I'm talking about absolute value, that means distance from 0. Negative 3 is 3 units from 0, so it's 3 units. Next line down, negative 25 plus 4 over 19. Negative 25 plus 4 is a negative 21 over 19 for my final solution. Factors and terms, when we're talking about algebraic expressions, algebraic factors and terms, factors are things that have, that are being added and factors are things that are being multiplied and divided. Terms are being added and subtracted. Looking here, these are being multiplied, so they're factors. This is being added, it's a term. These three are being multiplied, they are factors. This is being added, it's a term. This is being added, it's a term, but y squared is y times y, so technically y squared, each y is a factor, but y squared itself is a term. To simplify this, can use our properties to distributive property. This one distributes as well. Remember, that's a negative in the front, so I have negative 4 factor being multiplied times yz, so negative 4 yz. Then I'm going to have negative 4 times 3, which is negative 12. Keep track of your negatives really well. I'm going to have then negative 1. It's not written there as a negative 1, it's an implied negative 1. If it helps you, go ahead and write it in there as negative 1. So I can see it's negative 1 times 7yz, so negative 7 yz. Negative 1 times negative 1 is positive 1 plus y squared. Then when I get to simplifying now, I can only simplify terms that have the same exact structure to them. I have a yz, I have negative 4 yz's, or if I'm thinking about this, I have a whole that's negative 4 deep of the yz's. Do I have any other yz's? I do. I have other here. I also have negative 7 of those. So I have a grand total of negative 11 yz's. All right, I have a number 12. Do I have any just straight up numbers? I do. There it is. It's a 1. So I have a grand total of negative 12 plus 1, or I have a whole of 12 filling in a hole of 1, or filling in 1 foot of it. So now I'm at negative 11. And then I have, I'm just left with a y squared, so I'll have it plus y squared. We tend to like to write things mathematically in descending order, so I start with the highest power, y squared, and then I'll do negative 11yz, and then the thing without any variables goes at the end, minus 11. Finding this area of a rectangle, length times width. Two ways about going about this. We could just look at just this square if I wanted to, and say, well, this square is c by b, so it's going to be cb. And the other rectangle is a by b, so it's going to be ab, so my final answer is going to be ab plus cb. I could have also done it as the whole and said, well, this whole length is a plus c, that whole length there along that side, times the width is b, and then using distributive property, I would have a times b plus b times c, or c times b. Last thing for today, thanks for sticking with me here. All these properties of mathematics, commutative property means that if I have something like 8 plus x, I could rewrite it as x plus 8. They're the same thing. They commute around, just like when you commute from one place to the other. It's still the same thing. Additive identity, 9 plus 0 will just equal 9. So any number adding 0 to it, that's the additive identity. Additive inverse. Now it's the other way around. 9 plus negative 9 is 0. So what number, when I add it to its inverse, its additive inverse, it gives me 0. Distributive property, we did that on the previous one. We've done that a bunch of times in the past. Multiplicative identity, negative 7 times what number gives me negative 7? And the answer to that is 1. The multiplicative identity. You multiply something by itself, you get itself. Multiplicative property of 0, you're probably catching on to this. Negative 7 times 0 is 0. Any number times 0 is 0. Even 0 times 0 is 0. Multiplicative inverse. Now we're saying, if I have like negative 3, what can I multiply this by to get 1? And the answer will be the multiplicative inverse, or we call that the reciprocal, negative 1/3. Negative times negative is positive. And the associative property, a plus b plus 3x. If I do this, right now, And since it's all addition, I can just reorganize that as a plus b plus 3x. And that's the same. It's like, who do you associate with? And as long as they still remain equal to one another, then your association is valid. It gets messed up when there's maybe some negatives in there. So you got to be careful. If a negative is in there, how do you kind of distribute it out of a parenthesis so that when you finish it out and distribute it back in, you get the exact same thing. There it is. Quick review of chapter 1.